Hello, and welcome to Z Science, a quiet corner of the universe where curiosity slows down. Maybe you've had a long day, and the noise of it still hums somewhere in the background. Maybe the lights are dim now, the world outside has softened, and there's a little more room to breathe. This space is for that in-between time, when your body is ready to rest, but your mind still wants to wander. Here, science isn't about speed or precision. It's about awe, the kind that lingers like starlight. We'll drift through galaxies and atoms, through gravity and silence, through everything that makes the universe hum. You don't have to understand every detail. You don't have to stay awake till the end. You can simply listen and let the questions dissolve into calm. Because wonder doesn't need noise, it just needs space. So settle in, let the world fade for a while, and let's fall gently into the science of stillness. Because sometimes the most interesting thoughts are the ones that arrive softly, when we're too relaxed to question them too quickly. Tonight, I wanted to talk about something that has puzzled scientists, mathematicians, philosophers, and children alike for a very long time. The idea that the universe might go on forever, and yet also that it might have an edge. At first, those two things don't seem like they should belong together. They almost cancel each other out. How could something that's infinite have any kind of border? Doesn't infinite mean it just keeps going and going without interruption, without edges, without walls or boundaries? It seems like one of those questions that's either too obvious to ask or too impossible to answer. But here we are, asking it anyway, because asking questions like this is kind of what humans do best, especially at night, when the world slows down enough for those questions to bubble up. So we'll sit with it. You and I will turn it over, not to force an answer out of it, but to explore what the question is really made of, to understand what we even mean when we say things like infinite or edge or the universe. Sometimes just understanding the shape of a question is enough. But before we float too far into all of that, let me ask you something simpler. What time is it where you are? Not because I need to know, but because it's a nice way to remind ourselves that space isn't the only thing we're moving through. You're living in a time right now, a little moment in the great stretch of history and future and everything in between. And this moment, your moment, is the only one like it. Right now, as you hear this, the rest of the universe is still doing what it does. Galaxies are turning, stars are forming, comets are swinging through the darkness. But this second, this minute, this little pause in your evening, it's just for you. That's special in a quiet kind of way. If you're already feeling relaxed or curious, or maybe just barely staying awake, I'd love it if you gave this video a gentle like. Maybe even subscribe if sleepy science stories are something you want to keep nearby. I always enjoy hearing where people are listening from a small town, a busy city, a forest cabin, or just a bedroom with a soft blanket and a dim lamp. If you want to share that in the comments, I'd be grateful. It's like watching a little constellation of listeners light up around the world. It makes the universe feel slightly more connected, just slightly. And I'll say this too, as always, this video is meant for relaxation and curiosity. It's not a substitute for medical advice or treatment, and it won't fix insomnia or anxiety by itself. But maybe it can give your brain something gentle to focus on, something to wander through while your body winds down. That's my hope, at least. So, let's begin slowly. No pressure, just thoughts. You're lying there, maybe looking at the ceiling, or maybe just feeling the weight of the bed holding you gently. And maybe, like so many people have over the years, you've wondered what's beyond all this. not just the walls of your room or the edge of your city, but the real beyond, the kind that lives above the clouds, past the stars, outside of everything. The kind of beyond where telescopes point and never quite reach the end. Maybe you've heard the phrase, the edge of the universe, and imagined it like the edge of a map. The place where the stars just stop and there's a kind of blankness or a black wall or maybe a shimmering curtain. Maybe you've pictured someone flying a spaceship and reaching that edge like hitting the end of a highway, unsure whether to turn around or push forward. And then someone says the universe is infinite and that idea evaporates. Infinite means no edge, doesn't it? No stopping point, no boundary, just endlessness. And yet, the thought of infinity is just as strange. It's not something we encounter in daily life. You can imagine a big number, a really big one, bigger than the number of people on Earth, bigger than the number of grains of sand on every beach. But infinity isn't a big number. It's not even a number at all. It's a concept, a direction that never ends, a road with no final exit sign. So how can both of these ideas be true at the same time? How can the universe be infinite and still have an edge? The funny part is no one really knows for sure, at least not yet. But we've come up with ways to talk about it, to model it, to explore the possibilities. Some of those ways are mathematical, others are philosophical. Some come from astronomy, from real observations and data gathered by satellites and telescopes. Some are theories we've tested, and some are still ideas we're trying to understand. But they all orbit the same mystery. What is the universe shaped like? And what does that shape mean for where it ends or doesn't? When we ask about the edge of the universe, we have to be careful about what we mean. Do we mean the edge of space, the furthest point you could go if you just kept moving? Or do we mean the edge of time, the beginning or the end of existence itself? Or are we really asking about something even more basic? Like whether there's a place where things just stop, a wall, a border, a point where space itself can't go any farther. That's where we'll go tonight, slowly, one thought at a time. We'll talk about shapes, about the curvature of space, the expansion of the universe, the meaning of horizons, and how our small, time-bound perspective shapes the questions we ask. We'll imagine walking in a straight line across an infinite landscape. We'll ask, what happens if you never turn, never stop, never run out of ground? Do you ever return to where you started? Do you find a wall, or do you just keep going forever? But not all at once. We'll take our time, because part of understanding infinity is realizing that it doesn't rush. It's patient, like space itself. So wherever you are, however your day has gone, whatever thoughts are still lingering in your head, just let them slow down. You don't have to push them away. Let them drift like static behind the stars. We'll talk now, quietly, about something very big. You can start by picturing a room, a normal room. It has walls, a ceiling, a floor. You can stand in it and touch the boundaries. It's a closed space. You know when you've hit the edge. Now take away the walls. Leave just the floor, a flat surface stretching in every direction. You start walking straight ahead. No obstacles, no turns. You keep walking and walking and walking. You don't tire. Time doesn't pass in the usual way. You're just always moving forward. Eventually, you might start to wonder, will you hit something? Will you fall off? Will you reach a wall? Or will the floor just keep going forever? And what if, somehow, after an unthinkable amount of time, you find yourself arriving back where you started without ever turning around? What would that mean? that the floor loops, that space is curved, that you've been walking on the surface of something without knowing it. Now zoom out. Replace the floor with the universe itself. Replace your steps with the motion of light or gravity or galaxies. What is the shape of that space? Is it flat? Is it curved like a sphere? Like a saddle? Is it open? Or does it wrap around in dimensions we can't quite picture? We're getting ahead of ourselves, but only just. Tonight, we're not looking for a finish line. We're just walking, talking, asking. And as we do, we'll discover that infinity isn't what we thought, and neither is an edge. Let's imagine the shape of stillness. It might seem like a contradiction. Shape suggests structure, outlines, edges. Stillness feels like the absence of all of that. No movement. No form shifting into something else. Just a moment suspended without change. But if the universe is our setting, and space itself is what we're trying to understand, then stillness has a shape too. Even if it's too large to draw, too slow to notice, too quiet to feel. When people think of space, they often picture it as flat. Not flat like a table or a sheet of paper, exactly, but flat in the way that lines stay straight and angles behave the way they were taught to in school. If you draw a triangle on a flat surface, its angles always add up to 180 degrees. If you walk in a straight line, you never curve back around. That's flat space, the kind of geometry we're used to, where shapes behave predictably and distance works the way you expect. But space doesn't always behave like that. Not on large scales. Not when you start asking questions about the whole universe. Imagine again that you're walking in a straight line across a vast, featureless landscape. You're careful. You never turn. You keep your eyes fixed ahead, taking step after step. If space is truly flat and infinite, you'll never return to where you started. You'll keep moving forever, passing new territory that never repeats. But if space is curved, even slightly, then something strange might happen. You could walk forever and eventually loop around, coming back from the other side. Not because you turned, but because the space itself curved behind you. That kind of space has a shape, even if you can't see it from inside. It might not have a center. It might not have an edge, but it still has geometry, a way that paths behave, a way that movement unfolds over time. The most common metaphor for this is the surface of a sphere, like the skin of a balloon. From where you stand, it feels flat. You can walk in a straight line in any direction, but keep going long enough and you'll return to your starting point. The surface has no edge, but it's finite. There's only so much area. The horizon always moves with you, but you'll never find a boundary where it ends. And yet, that's just a metaphor. The real universe isn't a two-dimensional surface wrapped around a three-dimensional shape. The universe, as far as we know, has three spatial dimensions: forward and backward, left and right, up and down. If it's curved in a way that's harder to picture, a way that happens in 4 dimensions or more. And that's where our imagination starts to falter. We can describe it mathematically. We can write equations, draw graphs, simulate behaviors on computers. But we can't hold the shape of the universe in our heads the way we can picture a globe or a map or a circle drawn on paper. Even so, the shape is there. It determines how galaxies drift apart, how light bends around gravity, how the earliest ripples of the cosmos spread out after the Big Bang. The shape of stillness, in this sense, is the background against which all motion happens. We usually don't notice it because we're focused on the things moving within it: the stars, the planets, the expanding galaxies. But just like the surface of a calm lake shapes how ripples travel, space itself influences how everything behaves. So what do we know about that shape? Not much, but more than we used to. Astronomers have measured the cosmic microwave background, the faint glow left over from the early universe. It's not light from stars or galaxies. It's older than that. It's the afterglow of everything cooling down after the Big Bang. And hidden in that glow are tiny fluctuations, tiny patterns that tell us something about the universe's shape. Not directly, not by drawing it out, but by measuring how those patterns spread across the sky. From those measurements, the current evidence suggests that the universe is very close to flat. Not perfectly, not absolutely, but close enough that if it is curved, the curve is too slight for us to detect so far. That might mean space goes on forever in every direction. Or it might mean that it curves back on itself so slowly that the loop is bigger than we can observe. And that brings us to an important idea. We don't actually see the whole universe. We see the observable universe, the part from which light has had time to reach us since the beginning. The rest, if there is a rest, lies beyond our reach. Not because it's hidden, but because the light from those places hasn't arrived yet. And it may never arrive, depending on how far space is expanding. So when we talk about the shape of the universe, we have to remember that we're talking about the shape of what we can see. Maybe that shape continues. Maybe it repeats. Maybe it ends. We don't know. But if the observable universe is flat, and if space continues in the same way beyond what we can detect, then it might mean that the whole universe is flat, too, and infinite. No boundaries, no edges, just endless space. Or it could mean that we're just looking at a small patch of a much larger shape, like mistaking part of a curve for a straight line because you can't see the whole arc. If that's the case, the universe could still be curved and finite. It could wrap back around in a shape we can't quite grasp. And that leads to another thought. If the universe is curved, and you keep traveling in a straight line and eventually come back to where you started, does that mean there's no edge? Does that make it more or less infinite? You've circled back. The space repeated. But you never reached a wall. So in a way, that's still edgeless, still unbounded, just not infinite in the way we first imagined. It gets trickier when we ask how to measure any of this. What does it mean to measure the size of space itself, when space is also what defines size? If you're inside the universe, which we aren't, you're using space to define space. It's like trying to measure a ruler with itself. You can compare distances within it. You can chart the separation between galaxies. But you can't step outside and look at the shape from above. There is no above. The universe includes everything. There's no external viewpoint, just perspectives from within. That's part of what makes the question so strange. If you're inside something that might be infinite but might not be, and you can't get outside it, how do you even begin to know what shape it has? You can only look around, collect data, and try to piece together the pattern from the inside out. Still, the idea of shape matters, not because we expect to draw it on paper, but because the shape tells us how the universe behaves. If it's positively curved, like the surface of a sphere, then light travels in loops. If it's negatively curved, like a saddle, then light diverges, spreading out faster than you'd expect. And if it's flat, then light travels in straight lines, least straight in the context of the universe's own geometry, in everyday life. We don't notice these distinctions. The scales are too large. The effects are too subtle. But on cosmic scales, they matter. They determine how the universe evolves, how fast it expands, whether it will keep expanding forever or eventually collapse, whether the structure of space allows for parallel lines to stay parallel, drift apart, or bend together. And that structure, that shape, it's always there, even when everything else seems still, even when galaxies drift apart so slowly we can't feel the change, even when the sky above your house looks exactly the same night after night. The shape of space is the stage on which all those still moments happen. It holds the quiet, it shapes the stillness, and it may also shape the answer to our original question. Because if space has a shape, whether curved or flat or something stranger, that shape might tell us whether there's an edge, or whether the idea of an edge even makes sense. So far, there's no evidence of a wall, no sign of a boundary where things stop. But there is evidence of structure, of rules, of geometry. And that geometry may be the key to understanding where we are, and what it means to move through something that doesn't end and still wonder where it begins. Let's imagine the shape of stillness. It might seem like a contradiction. Shape suggests structure, outlines, edges. Stillness feels like the absence of all of that, no movement, no form shifting into something else, just a moment suspended without change. But if the universe is our setting, and space itself is what we're trying to understand, then stillness has a shape too. Even if it's too large to draw, too slow to notice, too quiet to feel. When people think of space, they often picture it as flat. Not flat like a table or a sheet of paper, exactly, but flat in the way that lines stay straight and angles behave the way they were taught to in school. If you draw a triangle on a flat surface, its angles always add up to 180 degrees. If you walk in a straight line, you never curve back around. That's flat space, the kind of geometry we're used to, where shapes behave predictably and distance works the way you expect. But space doesn't always behave like that. Not on large scales. Not when you start asking questions about the whole universe. Imagine again that you're walking in a straight line across a vast, featureless landscape. You're careful. You never turn. You keep your eyes fixed ahead, taking step after step. If space is truly flat and infinite, you'll never return to where you started. You'll keep moving forever, passing new territory that never repeats. But if space is curved, even slightly, then something strange might happen. You could walk forever and eventually loop around, coming back from the other side. Not because you turned, but because the space itself curved behind you. That kind of space has a shape, even if you can't see it from inside. It might not have a center, it might not have an edge, but it still has geometry, a way that paths behave, a way that movement unfolds over time. The most common metaphor for this is the surface of a sphere, like the skin of a balloon. From where you stand, it feels flat. You can walk in a straight line in any direction, but keep going long enough and you'll return to your starting point. The surface has no edge, but it's finite. There's only so much area. The horizon always moves with you, but you'll never find a boundary where it ends. And yet, that's just a metaphor. The real universe isn't a two-dimensional surface wrapped around a three-dimensional shape. The universe, as far as we know, has three spatial dimensions: forward and backward, left and right, up and down. If it's curved in a way that's harder to picture, a way that happens in 4 dimensions or more. And that's where our imagination starts to falter. We can describe it mathematically. We can write equations, draw graphs, simulate behaviors on computers. But we can't hold the shape of the universe in our heads the way we can picture a globe or a map or a circle drawn on paper. Even so, the shape is there. It determines how galaxies drift apart, how light bends around gravity, how the earliest ripples of the cosmos spread out after the Big Bang, the shape of stillness. In this sense, is the background against which all motion happens. We usually don't notice it because we're focused on the things moving within it, the stars, the planets, the expanding galaxies. But just like the surface of a calm lake shapes how ripples travel, space itself influences how everything behaves. So what do we know about that shape? Not much, but more than we used to. Astronomers have measured the cosmic microwave background, the faint glow left over from the early universe. It's not light from stars or galaxies. It's older than that. It's the afterglow of everything cooling down after the Big Bang. And hidden in that glow are tiny fluctuations, tiny patterns that tell us something about the universe's shape. Not directly, not by drawing it out, but by measuring how those patterns spread across the sky. From those measurements, the current evidence suggests that the universe is very close to flat. Not perfectly, not absolutely, but close enough that if it is curved, the curve is too slight for us to detect so far. That might mean space goes on forever in every direction. Or it might mean that it curves back on itself so slowly that the loop is bigger than we can observe. And that brings us to an important idea. We don't actually see the whole universe. We see the observable universe, the part from which light has had time to reach us since the beginning. The rest, if there is a rest, lies beyond our reach. Not because it's hidden, but because the light from those places hasn't arrived yet, and it may never arrive, depending on how far space is expanding. So when we talk about the shape of the universe, we have to remember that we're talking about the shape of what we can see. Maybe that shape continues. Maybe it repeats. Maybe it ends. We don't know. But if the observable universe is flat, and if space continues in the same way beyond what we can detect, then it might mean that the whole universe is flat, too, and infinite. No boundaries, no edges, just endless space. Or it could mean that we're just looking at a small patch of a much larger shape, like mistaking part of a curve for a straight line because you can't see the whole arc. If that's the case, the universe could still be curved and finite. It could wrap back around in a shape we can't quite grasp. And that leads to another thought. If the universe is curved, and you keep traveling in a straight line and eventually come back to where you started, does that mean there's no edge? Does that make it more or less infinite? You've circled back. The space repeated. But you never reached a wall. So in a way, that's still edgeless, still unbounded, just not infinite in the way we first imagined. It gets trickier when we ask how to measure any of this. What does it mean to measure the size of space itself, when space is also what defines size? If you're inside the universe, which we aren't, you're using space to define space. It's like trying to measure a ruler with itself. You can compare distances within it. You can chart the separation between galaxies. But you can't step outside and look at the shape from above. There is no above. The universe includes everything. There's no external viewpoint, just perspectives from within. That's part of what makes the question so strange. If you're inside something that might be infinite but might not be, and you can't get outside it, how do you even begin to know what shape it has? You can only look around, collect data, and try to piece together the pattern from the inside out. Still, the idea of shape matters, not because we expect to draw it on paper, but because the shape tells us how the universe behaves. If it's positively curved, like the surface of a sphere, then light travels in loops. If it's negatively curved, like a saddle, then light diverges, spreading out faster than you'd expect. And if it's flat, then light travels in straight lines, least straight in the context of the universe's own geometry. In everyday life, we don't notice these distinctions. The scales are too large. The effects are too subtle. But on cosmic scales, they matter. They determine how the universe evolves, how fast it expands, whether it will keep expanding forever or eventually collapse, whether the structure of space allows for parallel lines to stay parallel, drift apart, or bend together. And that structure, that shape, it's always there, even when everything else seems still, even when galaxies drift apart so slowly we can't feel the change, even when the sky above your house looks exactly the same night after night. The shape of space is the stage on which all those still moments happen. It holds the quiet, it shapes the stillness, and it may also shape the answer to our original question. Because if space has a shape, whether curved or flat or something stranger, that shape might tell us whether there's an edge, or whether the idea of an edge even makes sense. So far, there's no evidence of a wall, no sign of a boundary where things stop. But there is evidence of structure, of rules, of geometry. And that geometry may be the key to understanding where we are, and what it means to move through something that doesn't end and still wonder where it begins. So what do we mean by edge? It sounds like such a simple word. Most of us learned it early on the edge of the table, the edge of a book, the edge of a cliff. It's where something ends, where one thing stops and something else begins, usually nothing, or air, or a fall. Edges are clean and clear, defined by contrast. Inside the lines is the object. Outside is not. We use the idea of edges all the time, often without thinking about it. The edge of the city, the edge of the forest, even the edge of an ideatha. Point where what we understand blurs into what we don't. We're comfortable with edges because they help us feel oriented. They create boundaries. They separate what's contained from what isn't. But when we ask whether the universe has an edge, we're not talking about something that fits on a table or inside a box. We're asking whether all of existence, space, time, matter, and light could somehow have a boundary. And if it does, what would be beyond that boundary? And if it doesn't, how do we make sense of that? It's hard to picture a thing that includes everything and still has an outside. Because outside implies something else, something additional. But if the universe contains all space, then there shouldn't be an outside at all. An edge, in that context, would be a line beyond which there is what exactly? Not space, not time, not emptiness, because even emptiness is still space. So what then? A kind of non-place, the absence of having anywhere to go. That's where the familiar meaning of edge starts to fall apart. Because, in a physical sense, an edge only really exists in relation to what's on the other side of it. A book ends where the air begins. A sidewalk ends where the street starts. But the universe doesn't sit on a background. It's not placed on top of something else. It is the background. It's the space in which other things happen. So when we ask about an edge to the universe, we're really asking one of two things. Either, is there a point past which space doesn't continue a literal outer limit? Or is there some fundamental transition, a change in structure or conditions or the rules themselves that marks the end of here and the beginning of something other? That second kind of edge is more subtle. It's not a wall or a barrier. It's more like a threshold, You might not see it or feel it, but past a certain distance, the nature of reality could be different. Maybe the physics changes. Maybe the structure of space isn't the same. Maybe there are regions of the universe with different constants, different particles, or different dimensions. There are theories that suggest such things. Some versions of cosmic inflation, the theory that the universe expanded extremely rapidly right after the Big Bang, that our observable universe is just one bubble in a much larger multiverse. Each bubble might be a self-contained universe with its own laws. In that case, there might be a kind of edge, not a hard wall, but a boundary between bubbles or a region of transition. But we don't have evidence for that. Not yet, and that raises another point. When people hear the word edge, they often imagine a place you could go, somewhere you could travel to a location. You reach the end, you look over the side, and you see something, or nothing, or maybe you fall. But that assumes space works like a landscape, that it's a fixed terrain you can move across. In reality, space is dynamic. It expands, it curves. It's not a surface laid out on a table. It's part of the system, and your movement through it is shaped by its structure. So let's consider a simpler analogy. Imagine a video game. Not the characters on screen, but the code that defines the world. Maybe the game world is a giant square, and if you walk to the edge, you hit an invisible barrier. That's one kind of edge, the hard limit of the system. Nothing exists beyond it. Not even in theory. The developers didn't program it. Or maybe the world wraps around. You walk east, and after a long time, you appear back on the west side. That's another kind of edge, a boundary that loops. It's not infinite, but it has no stopping point either. You never hit a wall. You just repeat. Or maybe the game world generates more terrain as you explore, creating new space dynamically. From inside the game, it feels infinite. But from outside, from the perspective of the program, it's still limited. It only exists as far as you've gone. Now bring that idea back to our universe. We don't know whether it's a closed system, like the first example, or a looping one, like the second, or a generative one, like the third. But we do know that from our perspective, there is no observed barrier. Light comes to us from billions of light years away. Space continues in all directions, at least as far as we can measure. But even our measurements are limited. The speed of light gives us a horizon, maximum distance we can see. Not because there's an edge there, but because light from beyond that point hasn't had time to reach us yet. We call this the observable universe. It's like being in a fog. You can only see so far, but that doesn't mean the world ends at the fog's edge. It just means you can't see past it. Maybe there's more, maybe not. That idea, the observable horizon, is sometimes mistaken for a literal boundary, but it's not. It's just a limit set by time and the speed of light. The universe might extend far beyond it, or it might not. We don't know. But here's the part that often gets missed. If the universe does have an edge, it's not something we could ever reach in a conventional sense. Not because it's too far away, but because of how space itself behaves. The universe is expanding, not into anything, just expanding. The space between galaxies is stretching, and the farther away something is, the faster it recedes from us. At a certain distance, over 16 billion light-years, things move away faster than light. Not because they're breaking any rules, but because the space between us and them is expanding so rapidly. That means even if you could travel at light speed, you'd never catch up. You'd never reach those regions. They're forever out of reach, beyond the cosmic horizon. That's another kind of edge. Not a wall, not a place, but a limit on what can ever be known, ever touched, ever influenced. And yet, that limit changes over time. The observable universe grows as light from more distant places arrives. Our horizon expands. The edge shifts. So when you lie back and wonder whether there's an edge to the universe, the answer depends on how you define edge. If you mean a place where space ends, no, we haven't seen anything like that. If you mean a horizon beyond which we can't see, then yes, but it's not a boundary in the usual sense. And if you mean a fundamental change in conditions, a region where the universe transitions into something different, then maybe. But we have no proof yet. Most importantly, the edge isn't something fixed. It's not waiting for you to find it. It's not marked by a sign or a sudden drop-off. It's a concept that changes depending on your frame of reference, your tools, your definitions. It might be more useful to stop thinking about the edge as a location and start thinking of it as a relationship between what's known and what's unknown, between what we can see and what we can't, between what exists for us and what exists beyond us. That's what makes the question so rich. It's not about finding a wall. It's about understanding what it means to reach a limitant, what lies just past the edge of knowing. And as we move forward, we'll turn to one of the most misunderstood ideas of all, infinity. What is it, really? How does it differ from the merely large? And can something be infinite and still have no edge? Infinity isn't a number. We use it like one sometimes in casual conversation, in jokes, in exaggerations. We say something takes forever, that there are infinite possibilities, that the universe is infinitely large. And in those moments, the word usually just means a lot, more than we can count, bigger than we can handle. But in science and mathematics, infinity isn't just a bigger number than all the others. It's something different. It's not part of the counting system. You can't measure it with a ruler or reach it by adding one more and one more and one more again. It's not what you find at the end of a long line of zeros. It's what lies beyond the idea of endings altogether. If you take a calculator and type in a number that's too big for it to display, you might get an error message. But infinity isn't an error. It's a concept, a definition of It's what you get when you say something never stops, never finishes, never runs out. It's not 10 billion, or a Google, or even a Googleplex. Those are still numbers. They have places. They can be written down. Infinity never arrives. It's a direction, not a destination. This is part of why people get tripped up when they hear scientists say, the universe might be infinite, because it sounds like it should be measurable. If something is infinite, then surely we should be able to talk about how big it is, or how much it contains. But infinity doesn't work like that. You don't measure it. You approach it. You describe the conditions under which something grows without bound. It's not the thing. It's the behavior in math. You might see a statement like as x approaches infinity. That doesn't mean x becomes infinity. It means x gets larger and larger without limit. The process is the point. Infinity is never reached. It's what lies at the end of a pattern that has no end. And that's where things start to feel strange. Because in the real world, we don't deal with things that are truly infinite. We have large, we have small, we have fast, we have slow. But we don't have actual infinity. There's nothing you can point to and say, this here is infinite. Even the sky, which feels endless, is full of objects we can count and measure. Even the sea, which seems to stretch forever, has boundaries, depths, and limits. So when we talk about the universe being infinite, we're making a statement not about size in the traditional sense, but about structure. We're saying that as far as we can tell, there's no edge, no limit, no sign of stopping. The geometry of space is such that it continues and continues and continues again. This doesn't mean the universe contains every possible thing. It doesn't mean that somewhere out there every version of reality plays out. It simply means that space itself, the fabric of the cosmos, might extend without bound. That you could keep moving in a straight line and never come back around, never hit a wall, never find a final star at the edge of creation. But here's where it gets even more subtle. Something can be finite and still have no edge. Think of the surface of a sphere again. It has a total area. You can calculate it. But there's no boundary, no cliff, no end. You can walk in any direction and never fall off. That's a finite surface with no edge. Now imagine that in more dimensions, a universe that wraps around on itself in ways we can't picture. It might be finite in volume, but unbounded in experience. You'd never find a border because there isn't one. You just keep going over and over, always forward, never stopping. That's different from an infinite universe, but it feels similar. Both are edgeless. Both let you keep going, but one loops, the other doesn't. And that's why the difference between infinite and edge-free is important. You can have one without the other. Just because there's no edge doesn't mean the universe is infinite. And just because the universe is infinite doesn't mean it contains everything you can imagine. When scientists try to determine whether the universe is infinite, they look at clues, the curvature of space, the way light behaves, the distribution of galaxies. And based on what we see, the universe appears to be either flat or very close to flat. If it's exactly flat and it doesn't loop back on itself, then it probably is infinite. Not because we've measured every corner, but because the geometry implies it never folds back. It just keeps going. But remember, our observations are limited. The observable universe is a sphere around us, about 93 billion light-years across. That number can be misleading. The universe is 13.8 billion years old. But because space itself expands, the edge of what we can see is farther than that. Light has been traveling all that time, and the fabric it's moved through has stretched. Still, that 93 billion light-year span isn't an edge. It's a horizon, a place beyond which light hasn't had time to reach us. What lies beyond it is unknown. And that unknown space might be part of an infinite whole. Or it might be a patch in a larger but finite universe. There's no way to know, at least not yet. Some people struggle with the idea of infinity because it feels too big, too abstract. It doesn't behave like things we know. But that's okay. You don't have to visualize it all at once. You can just understand it as a kind of openness, a system without walls, a space where there's always more space. That's enough, and it's worth saying this too. Infinity doesn't mean chaos. It doesn't mean anything can happen or that everything does happen. It just means there's no upper limit on the extent of the system. It could still be ordered, still follow rules, still evolve. Infinity doesn't erase structure. It just removes the fence. In fact, some infinities are bigger than others. That sounds strange, but in mathematics, it's well established. The set of natural numbers, 1, 2, 3, and so on, is infinite. So is the set of real numbers between 0 and 1. But there are more real numbers than natural ones. Different kinds of infinity. Different sizes of the unbounded. That kind of thinking helps mathematicians reason about sets, limits, and continuity. In physics, it's harder to apply because we don't just want to know whether the universe is infinite. We want to know what that means for us, for our location, for our future, for the shape of space and time itself. And this leads to something deeper. If the universe is infinite, then the observable part, the bit we can see and measure, is just a small patch, an island in a much vaster ocean. And if that ocean continues without end, then it raises more questions. Are the physical laws the same everywhere? Is matter evenly distributed? Are there parts of space that look nothing like our own? We don't know, but we can guess. Based on what we see, the universe looks remarkably uniform on large scales. That suggests that our patch is not unique, that the rest of the universe, infinite or not, probably follows the same rules. But again, we can't test that. Not directly, which means that even though infinity might be part of our model, it remains a placeholder, a way of saying we don't see a boundary, and nothing in the equations requires one. That doesn't mean there isn't one. It just means we haven't found it. And this, in a way, brings us back to the idea of edges. Because if the universe is infinite, then there's no edge by definition. But if it's finite and unbounded, if it loops, then again, there's no edge. So in either case, we're left with a strange conclusion. The universe might have no edge. Whether it's infinite or not, that's the part people tend to miss. The absence of an edge doesn't tell you whether space is infinite, and infinity doesn't guarantee the absence of a boundary. It all depends on the shape, the structure, the geometry, so maybe it's time to stop asking whether the universe is infinite, and start asking something more useful. What's the shape of the space we live in? How does it curve? How does it connect? How does it guide motion, light, and time? Because those are the questions we can begin to answer, not by looking for walls, but by watching how things move, how galaxies drift, how background radiation spreads, how gravity bends light. Let's start with the shape we understand best, the flat universe. When scientists describe it that way, they mean that on the grandest scales, the rules of geometry behave exactly as you learned them in school. Parallel lines never meet. A triangle's angles always add up to 180 degrees. Light moves in straight lines, unless gravity bends it near massive objects like stars or galaxies. In this model, space doesn't curve inward or outward. It simply stretches evenly in every direction. Flat space can still expand. In fact, that's what ours appears to be doing. The galaxies drift apart, the cosmic fabric stretches, and yet the geometry stays balanced. If you could zoom out far enough, you would never find a point where space turns back on itself or curves away into a saddle. It's neutral, perfectly poised between the two extremes. The next shape is the closed universe. This one curves inward, like the surface of a sphere, except not a two-dimensional surface, but a three-dimensional one. Try to imagine that. Every straight path you take, every beam of light, every journey that goes on long enough, would eventually loop back to its starting point. It sounds impossible, but that is how curvature works when space connects to itself in such a universe. There is no edge and no outside. You could travel forever and never fall off. You would just return from the other side. This kind of universe is finite. It contains a total, measurable volume, but that volume loops back around. There's no outer void to fall into, no rim or border. Everything exists within that single, connected structure. A closed universe would also have a particular destiny. Its own gravity would, over immense stretches of time, slow the expansion and eventually reverse it. The galaxies would stop drifting apart, start coming together again, and collapse inward. This hypothetical ending is called the Big Crunch. The universe would shrink, heating and compressing until everything returned to a single, dense state. The third possibility is the open universe. It curves the opposite way outward, like a saddle. In this model, space is unbounded. Lines that start parallel gradually diverge. Triangles have angles that add up to less than 180 degrees. Light traveling across it spreads more than expected. A universe shaped this way never loops back. It just keeps expanding. An open universe is infinite. Its expansion might slow, but it never stops. Over unimaginable spans of time, galaxies drift apart, stars die, and the cosmos becomes thinner, dimmer, and colder. Matter spreads so far that even heat itself evens out until there's no contrast, left only stillness. Scientists call that final state the heat death of the universe. It's not violent, not dramatic, just a gradual fade into perfect calm. These three shapes, flat, closed, and open, aren't just philosophical ideas. They come directly from Einstein's equations of general relativity. Those equations describe how energy and matter curve spacetime, how geometry and gravity are woven together. The shape of the universe, then, depends on its total energy density, how much matter, radiation, and dark energy it contains compared with a critical threshold. If the actual density equals the critical value, space is flat. If it's greater, the universe is closed. If it's smaller, the universe is open. So how do we measure something like that? Astronomers study the cosmic microwave background, the faint afterglow of the early universe. They map its tiny fluctuations, the patterns of temperature and density that ripple across the entire sky. Those ripples act like fingerprints of geometry. The way they appear tells us how space bends across vast scales. We also look at how galaxies cluster, how light bends around massive objects through gravitational lensing, and how distant supernovae appear fainter or brighter depending on how far they've been stretched by expansion. All of these clues add up to one consistent story. The universe appears flat, or so close to flat that any curvature is smaller than we can currently detect. That doesn't mean it's perfectly flat or infinite, only that within our horizon, within what we can observe, behaves as if it were. The difference between a slightly curved and a perfectly flat universe might be so subtle that it hides beyond our instruments' reach. But even a flat universe isn't simple. Flat space can still expand, still accelerate, still evolve. It can contain filaments of galaxies stretching across billions of light years, and vast empty voids where almost nothing exists. The flatness describes the backdrop, not the details, and the backdrop is influenced by what fills it, especially by dark energy. Dark energy is mysterious, invisible, and dominant. It makes up most of the universe's total energy density. We don't know what it is, only what it does. It drives the universe to expand faster and faster, as if there were an outward push built into the fabric of space itself. That push doesn't come from explosions or motion. It comes from the nature of space. The more space there is, the more dark energy there is, and the more expansion accelerates. A self-amplifying cycle of quiet, endless growth. In a flat universe filled with dark energy, expansion never stops. Galaxies drift apart, their light stretches and fades, and over billions of years, each one slips past the point where its light can ever reach us. Eventually, only our local cluster remains visible. Beyond it, darkness. No galaxies, no glow, no trace of the wider cosmos. It's strange to imagine that. A universe still vast, still expanding, but silent. The night sky empty. Yet, that emptiness would still be space, still geometry, still time flowing. So when people ask whether the universe is flat, open, or closed, the best answer for now is flat, with a margin of uncertainty. But even that answer depends on what we mean by space, by distance, by the measurements we make from within. It depends on light that left its source billions of years ago, on equations that describe curves we cannot see. Still, one thing is certain. None of these models, flat, open, or closed, require an edge. None of them include a wall, a boundary, or a place where space simply ends. The idea that the universe must stop somewhere ever appears in the math, which brings us back to where we began, to the way human minds imagine edges because everything we know has them. Tables, rooms, maps, planets. But the universe is not an object placed inside something larger. It is the something larger. It contains all directions, all points, all frames of reference. There is no outside to move into, no rim to reach. And so, whether space is flat, curved inward, or curved outward, it remains edgeless. You can travel as far as you like in your thoughts or in your equations, and you will never find a border marked here, the universe ends. The shapes might differ, the destinies might differ, but the absence of an edge is the one thing they share. Stop. End part 6. Now that we've seen how space can curve inward, outward, or not at all, there's a deeper question that waits quietly underneath all of this. How can something be finite and still have no edge? How can space be boundless, yet not infinite? At first, that sounds like a contradiction. Everything we encounter has limits. A table ends at its edges. A room stops at its walls. A planet's surface is enclosed by its own shape. Even the sea, which looks endless when you stand on the shore, is curved and held by the earth. We're used to boundaries. We rely on them to define things. But not everything needs one. Mathematically and physically, it's possible to have a space that is finite yet unbounded, a space that contains a limited amount of volume, but where you can travel endlessly without falling off or hitting a wall, a space that closes smoothly in on itself. And this might describe the universe we live in. Let's start with something simple. Picture a perfect circle drawn on a page. The line has a measurable length, its circumference, but no beginning or end. You can move along it forever and always return to where you started without ever stopping or turning around. That's a one-dimensional example of a finite, unbounded shape. Now take a step up. Imagine the surface of a sphere, like the surface of the Earth. That surface has an area that you can calculate, but it has no edge. You can walk or fly in any direction, and you will never find a border. You'll just keep circling. That's a two-dimensional example. Now, extend the idea once more into 3 dimensions. Imagine a 3-dimensional version of that sphere's surface, a space that curves back on itself in every direction. But without sitting inside a larger container, you can move straight ahead through it forever. And eventually you would return to where you began, though the journey would take longer than the universe has existed. That's a finite, unbounded space. We can't visualize it directly. Our minds are built for 3 dimensions, not 4. But the mathematics works, and so does the physics. You don't need to picture it to understand that it could be real in such a universe. There would be no outer wall, no final galaxy, no last coordinate. Everything would connect smoothly. No edge, no beyond. Everything included. This isn't science fiction. It's one of the models cosmologists seriously consider a closed universe, curved gently enough that we can't yet detect the return path. If it loops, the loop might be so vast that it's effectively invisible, larger than our observable horizon dot. From inside such a universe, the experience would feel infinite. You could look in any direction and always see more galaxies, more space, more time. But behind that apparent endlessness would be a structure, a curve that eventually brings every straight line home. This kind of geometry changes how we think about travel, light, and even history. In a finite but unbounded universe, a B. If space can be boundless and still finite, then what would it mean for it to have an edge at all? What would such an edge look like if it existed? Could you travel to it? Could you point at it, stand beside it, touch it? It's a question that sounds simple but quickly falls apart under its own weight. Because when we ask where the edge of the universe might be, we're using words shaped by our experience of living inside boundaries, fields that end, rooms with walls, planets with surfaces. We think in containers. But the universe isn't a thing inside a larger space. It is space. When you walk to the edge of a forest, you step into a field. When you reach the edge of the sea, there's land or air beyond. But if the universe contains all space, then there's nothing beyond it for the edge to open into. What would be on the other side? Not space, not air, not even emptiness, because emptiness is still a kind of space. Beyond an edge of the universe, there could be no beyond at all. The very concept stops making sense. Still, it's worth imagining, if only to understand why it doesn't work. Suppose we could send something, a beam of light, the fastest traveler possible, straight ahead into the dark, forever. It moves at light speed, unblinking, unstoppable. As it goes, space itself stretches beneath it. The light never slows, but the fabric it crosses expands. The farther it travels, the farther its destination recedes. Eventually, the expansion outpaces even the light. Not because the light breaks, but because space grows faster than the light can bridge it. That line, that unreachable boundary, where light can no longer make progress, is called the cosmic event horizon. It's not a wall, not a membrane, not a place. It's a limit built into the way space expands. Beyond it, light will never reach us, not now, not ever, from here. That horizon sits about 16 billion light-years away. Beyond that, galaxies exist, but their light, emitted today, will never arrive. They drift, untouched, in a part of the universe we will never see. The edge of our knowledge is not the edge of space itself. It's just the edge of what can ever be known. That's the first kind of boundary the universe gives us, a practical one. A horizon set by time and expansion. It shifts as the universe grows. Every moment, light from more distant places arrives, pushing our visible limit farther outward. But at the same time, new regions slip away beyond the event horizon, carried off by acceleration. The map of what we can see changes forever, yet the unseen remains vast and silent. If you could somehow follow that photon, it would never find a wall. it would never stop. It would move endlessly through expanding space, always finding new distances unfolding ahead. Unless, of course, the universe loops, but even that loop would be too vast to complete. And what if, for the sake of imagination, there really were an edge, a hard border between space and not space? What would that be made of? What would hold it up? If it's physical, then it exists in space, which means it's not an edge, just another region. If it isn't physical, then what could it even mean to reach it? There'd be no direction, no dimension left to move through. That's why cosmologists usually stop asking, where does space end? And instead ask, what does space do? The edges that matter aren't places. They're relationships between what's observable and what isn't, between what can be reached and what can never be touched. The universe doesn't stop, but our ability to interact does. That's its truest boundary. It's a strange kind of limit. Not one you could ever see, not one you could ever cross. It's a soft edge made of time, light, and distance. Beyond it, galaxies evolve, stars form, gravity pulls. But none of it will ever reach us. Every observer, everywhere, has their own version of this horizon. A sphere centered around them, about 46 billion light-years in radius, containing everything from which light has had time to arrive since the beginning. Each galaxy, each planet, each person lives at the center of their own observable universe. None are special. All are bounded by the same physics of light and time. Beyond those horizons, there is almost certainly more universe, more galaxies, more space, maybe more time. There's no sign that anything unusual happens at the edge of what we can see. The patterns we detect in cosmic radiation and galaxy distribution continue smoothly, as though space simply keeps going. There's no sudden cutoff, no visible border, just the silence of light that hasn't had enough time to reach us yet. We assume that the universe beyond looks much like what we can see: uniform, balanced, governed by the same laws. It's a reasonable assumption, supported by everything we've observed so far. But it's still an assumption. Beyond our horizon, we can't measure, can't verify, can't know. That part of the universe, if it exists, is forever disconnected from us. This is the difference between the observable universe and the universe itself. The observable one is the part we can see, bounded not by space but by time. The timelight has taken to travel since the Big Bang. The full universe may be vastly larger. It might even be infinite, but we'll never know for sure. Not because we haven't looked far enough, but because there is no way to look far enough. That's not defeat. It's just the nature of space and time. There are things the universe will never allow us to see, and still, we can infer their presence from the echoes and patterns that reach us. So when we talk about the edge of the universe, we are really talking about the edge of understanding, the point where data stops and imagination begins. Beyond that edge may lie more of the same, or something profoundly different. But from here, it is forever invisible. The universe's expansion carries it all beyond reach. Galaxies that are visible today will one day fade, not because they vanish, but because their light will never arrive again. The horizon will close behind them, and their existence will continue only beyond our sight. That's the quiet, gentle paradox of cosmic scale. The more we learn, the more we realize how much of it will always remain hidden. Yet, somehow, knowing that is its own kind of peace. The understanding that the unknown will always be larger than the known, and that mystery itself is part of the structure of everything.